Hello, welcome if you are new here to Decaf Math, and welcome back if you are returning. I thought that we could go into some more Gaussian elimination today. So this is a concept from linear algebra. This style of video, if you've been around, you'll know, is not so intentionally sleepy, though I do plan to make sleepy math videos at least once a week. But this is more just like us hanging out, just relaxed, taking things nice and slowly. This gives me a way to get some feedback from people who are watching my videos for the math. And I hope that these kinds of videos are more just like chill and helpful, and just geared for people who are actually studying this stuff or who would be interested in studying. And it also gives me a chance to review as well. So this is just more of our relaxed paced, but not necessarily intentionally sleepy. But if you do get kind of drowsy, feel free to drift off to sleep. It's totally okay, unless you need to be awake. But I'm just your math buddy right now, and thanks for hanging out with me. So we've already started this, I guess we could call it a series, but working with systems of linear equations. So in this case, we have 3 equations and 3 variables, x, y, and z. And we've already talked about how to represent that system as a matrix, so it's an augmented matrix. I'll try to have all this stuff linked down below, but you can also find it in my linear algebra playlist. And so basically we just keep things lined up. So this column is for coefficients for x, this is y, this is z, and the line is for the augmenting, and it represents like the equals, right? And then the 5, 6, and negative 15 are the right-hand sides, basically. So we have a 3 by 3, then we augment it to it, so we extend it to this 3 by 4. And so this matrix represents this system, right? So we've already gone over that. And we've also talked about row operations. So row operations are basically just things that we can do to the rows, so rules for the rows of these matrices. So in this case, like we said, this has 3 rows, that, just logically align with what we would normally do with solving this system algebraically. So the row operations that we set up were, like swapping. You can swap 2 rows, any 2 rows, and that's fine. That doesn't break math because that's just like swapping 2 equations in a system, and that doesn't change the system. We can scale a row, which just means that you multiply any row by a constant number, like each term in a row by any number. If you feel like a troll and you want to multiply by 0, you could, but that doesn't get you anywhere, so don't do it. But you could, for instance, you can multiply each term in this row by 2, and the reason you're allowed to do that is because that's the equivalent of multiplying by 2 on both sides of this last equation here, and you're allowed to do that because of the property of the equal sign. It stays balanced, right? But essentially when you do multiply both sides, you distribute that 2 to each of these terms, and that's the equivalent of multiplying by each coefficient by 2, and also on the right hand side as well. So that's why you're allowed to scale. And then I just wrote add I'll add a multiple here, but what I mean by that is, let's say you're trying to eliminate x from, equations 1 and 3, like you try and combine them to eliminate x. You could basically add -2 times equation 3 to equation 1, and you've gotten 0, like 2x minus the 2x here becomes 0, and then of course you have to distribute that out for the rest of the coefficients and the rest of the terms, but that's what it means to add a multiple. And that's the same for minus, because subtracting is adding a negative multiple, right? Okay, anyways, hopefully that made sense, but that's what it means to add a multiple. So I could do, that would be the equivalent of doing row 1 plus -2 times row 3, or just row 1 minus 2 times row 3. So that's one row operation as well. So we've already established 3, and when I kind of started introducing this idea, my emphasis was on relating these row operations, just these basic 3, to really what we're doing with just our regular algebra. And I think that that's more important because I think different professors and different texts write out the row operations differently. Like, there's subtle differences, and I think they're all equivalent. So these are the 3 that I've established, but it's ever slightly different, and let alone the notation. So as long as you can adapt, the idea, if you did see something like really different from, these 3, take some time to convince yourself that they are equivalent. And if you're still really stuck, let me know, and I'd be happy to take a look. But these are the main concepts, and you can kind of see how it's just, it's basically what you would normally do if you were trying to like eliminate a variable anyway when you're solving these like by hand. So this is like 3 variables, 3 equations, that's fine, but imagine if you're doing like a 10 by 10, like that's a lot, right? So we basically talked about these row operations, and we said we're going to take this matrix and use those row operations to try to get something into this form. This is actually what I wrote at the time. 1 0 0 0 1 0 0 0 1 stuff and stuff. And by stuff I mean it can be 1, it can be 0, but it doesn't have to be. So my hearts are cute, so but they can be any number, right? And so I said I'm gonna try and go from point A to point B, and we took our time with this to see that really, because everything stays lined up, so this is still X, Y, and Z. So essentially, if I get to this form, I'm basically saying, okay, Z, so the zeros cancel, right? 0x goes away, 0y goes away, because it's just 0 and 0. 0 plus 0 is still 0, plus 1 times Z is still Z. So this just tells me Z equals whatever that number is, Y equals whatever that number is, and X equals whatever that number is, right? So that's essentially our goal, is using operations. Now, for Gaussian elimination specifically, this is like super reduced, right? This tells us directly what X, Y, and Z are, which is what it means to solve, right? And we took our time to write this out, so feel free to check out those videos. But this is very, very reduced. This is like the most direct answer. Now, for Gaussian elimination, you don't have to go that far, and let me show you why. So you don't have to go quite to the point where you have zeros above here. You just actually need this form, which is called row echelon form. And I actually think that going into Gaussian elimination from what we've covered so far is a little bit of a jump. I know you can handle it, because I'm going to tell you that we have this staircase 1 1 1 in this particular form. But just given that information, we have enough to solve this problem. But I will go into row echelon form in a separate video with like all the actual rules for what it takes to be in row echelon form. But the idea here is we don't need zeros above these ones. It's like this little staircase, and in some texts even you don't even need one specifically, as long as you have a number, but you just need the zeros below. So the idea here is you can see, like, we have leading terms. I think the convention is to have ones. It's not hard to go from not ones to ones anyway, so just do that extra step. But if you get this form, this is fine, because if you continue to line things up like x, y, z again, this tells me that z equals some number. So again, each of these hearts can be any number. They can be zeros and they can be ones, but they don't have to be, right? So this tells me, again, working bottom back up, this tells me that z equals a number. And then once I get that number, I can plug that into the row above that, which would be y plus something z equals something. Well, I can plug that z value in and solve for y, because then I have one equation with one variable. Does that make sense? You're plugging into the row above. Then you have so you have y and you have z, and then you plug those values into the equation above that, which is x plus something y plus or minus, something z equals something. So you have your y and your z values, and you can plug those in and solve for x. So basically, if you have this form, you can just then substitute, like, this is like a downward staircase, like downward stairs, I guess. And here you just go back upwards to solve z, then y, and then x. So you don't have to go all the way reduced to zeros, where it's just x equals something, y equals something, z equals something. You can sort of work your way back up. So now our goal for Gaussian elimination is just to go from here to here, just because it's easier. And then once you get to here, you can just write it back out with algebra, and it's just one-step substitutions. So we can work through this example, okay? Okay, so for the rules for row echelon form, we'll definitely write that, because it's not always like one step like this. The basic idea is that these ones are like pivots, and like the leading term, which is, it's basically the first term that is not zero, that has to be it has to be to the right of the leading term of the row above it, if that makes sense, which is what leads to this pattern. And so since it's non-zero, like it's the first non-zero term, it means that everything before that has to be zero, if there is anything. Like this for this first row, the first non-zero term is that first one. But then in the second row, this first non-zero term is this one. And so, then the first term would be a zero. And so because of the property of that, you'll see that it basically combines or stacks up to mean that there are zeros below each of these pivots, if there is a row below it. And if there's like a row with all zeros, it goes on the very bottom. Okay, so again, I'll probably go into that more as like a strict definition in another video, but I wanted to start building the idea that we don't need to go all the way to like reduce it down. For Gaussian elimination, we just need to get to this basic form, okay? So how do we get there, right? So I think we're going to work through this specific example in another video, because this is going to get super long. But let me just lay out the general idea, and we'll work through the actual numbers in like a part 2. So first things first, we need to keep our row operations in mind. We need to set up our matrix. Gaussian elimination is like an algorithm, so it's just like a direct method to go from here to here. Because if you were to just rely on your intuition about going, okay, well, if I swap and I do this, you might actually end up going in circles because you might end up getting your ones in the diagonal, but if you don't have the zeros below it, you would just kind of not end up with something that's helpful, and you're just going to be working in circles. Like, you'll get a bunch of equivalent equations. You know, you might do, you know, equation 1 minus equation 3 and get an equivalent equation, but it doesn't do anything. So with this specific algorithm, it helps you do it in like a methodical order so that you're not just kind of getting equivalent things. Even though you have the ones, you might not have the zeros in the right place. And it's kind of like a Rubik's Cube, right? Like, you can get one face, but everything gets messed up if you kind of start doing another piece and mess with that first part. So let's see, the overall idea is, well, first of all, Gaussian elimination is named after the famous mathematician Carl, oh, I'm totally gonna butcher the spelling, Friedrich, I'm very partial to the name Friedrich, I think it's Friedrich Gauss, very famous. So yeah, Gaussian elimination named after him. And the idea is, what we're gonna do is go column by column. And that's actually not, I don't think that's necessarily like obvious. It might kind of seem obvious, like, you know, looking back, it's like we have this brilliant method, sure, but I don't think that that's necessarily obvious. I do like the concept of having these pivot points, because once you have zeros, they're nice to work with, because anything times 0 is 0, so if you add to it, it doesn't matter. Like, anything plus 0 is itself, so that's really nice. Once you have the ones, those are nice pivots because you can multiply by whatever you need it to be, rather than constantly, you know, like, you know, sometimes you have to like multiply this one by 4 and this one by 7, and it's just like a mess. But if you have 1, you just use that one as your pivot point, and that's nice. So I don't think this is necessarily like an obvious approach, but I think it's brilliant. So basically what you can do is, for Gaussian elimination, you start with, we're just going to go column by column and turn them into 1, 0, 0. So like this column, we're going to make this 1, 0, 0 first, do all the row operations that we need, swap scale, add a multiple, we'll kind of play around with that. Once we get that to 1, 0, 0, we're not going to touch that first row anymore. I mean, I don't think we really will, right? We can just get it to 1 something something something, and we'll have the zeros down here. Then we move to this column, and we just do these two because that one's already where it needs to be. That's fine. And we're going to make this 1 and this 0. But, you know, the numbers will be different once we mess around with this. And what's cool about that is, by the time you make this 1 and 0, these two will have already been like made to 0 because we're doing this and then this. And if these are 0, like I said, if you're multiplying by anything, you're adding anything, it doesn't change it. So that's super convenient. So once we get that, we'll probably get a number here. It may or may not be 0. Or 1, I'm sorry, not 0. It may or may not be 1, and if it's not 1, you can just scale that down to 1 so that we have our 1, and we just kind of do it column by column. And I think that's just sort of the basic idea of how the Gaussian elimination works, and the general idea is eliminating one variable at a time. If you think about it, if we're changing things to be 0, that's kind of like when we work through this algebra by hand. That's aside from, you know, substitution or little tricks that we might see, a very methodical way of doing it is to eliminate one variable at a time. And that's it. Okay, so that's the general idea. Now we can work through the numbers in this part too. I just kind of didn't want to shove this into like an hour-long video. Just if you're here for like a quick overview of how it goes, I kind of needed this reminder too. So anyways, that's like the big picture. We will definitely work through the numbers, but before we get really caught up in all of the steps and the row operations, I wanted to sort of remind you of this like big picture in case you're here to just kind of refresh if you've actually learned this before. That's the general idea, I believe. It has been a really long time for me as well, but this is how I remember it. And this is different from getting it all the way to reduced. I think that's where the Gauss-Jordan part comes in, but I'll need to review that as well. But anyways, we can definitely work through this example in a little bit, and that's what I'm gonna do. But I just didn't want to get like caught up in switching this and doing this, like why are we doing it? But remember, we start with column by column, and we're gonna do this as one first, get these zeros, then get this one, make this a 0, and then scale that. So stay tuned for that. Check out the next video. And I also just kind of wanted to remind you, like, let me know if you have a particular style of video that you like or a specific math topic, and we can still continue to play around with it. Some videos will be more sleepy time videos, and others will be more like this, where I'm just kind of casually half reviewing myself, hoping I can help someone else out there. And yeah, alright, I will see you in the next one for this. In part 2, I'll probably upload these at the same time, and on to some more math. Hope you have a wonderful day and night.